okay, your project is going to be to, what role do the biggies play in the carbon cycle? I'm like, oh man, can't you give me something that I'm already working on? He's like, no, you need to do stuff that you don't want to do. And I'm like, okay. So I had to, what are the roles, the big sharks, the big whales, the dolphin, what role do they play in the carbon cycle? It's really simple. They eat stuff. And when they eat stuff at the top, they swallow it and they swim down deep. And then when they go to the bathroom, they dump it and they get rid of it deep in the ocean. So instead of stuff dissolving at the top, they're eating, swimming back down, and burying carbon. And then you got the gelatinous looking stuff. Beautiful, the ctenophores and the jellyfish. This is all particles of marine snow, little phytoplankton that stick to their surfaces. And when they die, they swim really deep. When they die, they either die and bury, or they're consumed, and then whatever's consuming them, when they die or when they release their waste, they're burying it. So the pulling down effect is very, very important. All of these organisms play a role in regulating Earth's climate, controlling CO2 due to the presence of life. Life is controlling the climate. And what I mean by life, I mean by that upper millimeter of tablespoon of water. All those living critters, them eating each other and eating and pooping and bacterial remineralization is also important. Because remember, tied up in this web of life, you have bacteria. And that bacteria sits and eats the waste product of these organisms. And that bacteria helps break down the waste product, which is made of carbon. So without the bacteria, the viruses, all this interconnectivity, it's very important and it's very delicate ecosystem. And here's a nice cartoon I like because it shows again, CO2 in, you have small plankton being eaten by large plankton, microzooplankton, and the bacterial loop, the microbial loop. Remember, this component, this bacteria, very important because it sits on the coatings of the fecal matter. It sits on the coatings of dead stuff as it's floating down in that mucus floc and breaking down the carbon and burying it. And you got this loop, you got the carbon pump, you got the life loop controlling the carbon pump, and then come the fish, which feed our economies, which give people jobs, which is a source of protein for poor people in small island nations around the globe. Very, very important niche. And then you got the stuff that's being buried, and in every 1,000 years, you got this ventilation of CO2 coming up. It's a 1,000-year cycle, so right now you're breathing the air, you're breathing Viking air. So when the Vikings were around, that's the type of carbon that's eventually being upwelled, that was buried. The cycle was 1,000 years, so you're getting that CO2 right now that's off-gassing. So for every one, I don't want to say the word mole, but for every one molecule of CO2 going in, one is coming out, and it's balanced by photosynthesis. And this is the basic carbon cycle, just another. Where does the calcium come from? It comes from land. Rain brings it to the water. That calcium ions is in seawater. The marine biota take up that calcium, and you have productivity. But remember one thing. Let me ask a silly question. Where do trees get protein from? Trees get sugar, right? They sit in the sun. They make sugar. We know that. But where do they get? Every organism needs enzymes and proteins. So where do they get protein from? How? You're good. You're good so far. But go further. The roots are taking up what? They're taking up water and something else.
Minerals.
Thank you. Nitrogen. Miracle Grow. So, but remember one thing. So you got these, you mentioned these things, these three things. You got nitrogen plus light plus CO2. But how does the nitrogen get into the dirt and get broken down so the tree can eat the nitrogen? Bacteria. So the bacteria fix the atmospheric nitrogen, and you have Miracle-Gro already made on a silver platter. Here you go, Mr. Tree. You got your nitrogen. I just synthesized it, and I'm pooping it out, ready for you to eat. And that's what the bacteria do. So what about the air we breathe? 78% of the nitrogen in the atmosphere is in the form of dinitrogen, N2. Trees can't suck that stuff up. You need bacteria there. And guess what? Phytoplankton and diatoms, they also need enzymes. So they need Miracle-Gro too. So with the help of bacteria, the bacteria little phytoplanktoner, tiny little bacteria, atmospheric nitrogen comes into the water, the bacteria, nitrification, take it and make food, Miracle-Gro, for the little phytoplankton to live. So with light to make sugar and ammonium to make amino acids into proteins, this little critter has life. So without the presence of bacteria, we have a big problem. Nitrogen fixation requires low oxygen, high light, low nitrate. But I just want to show you some pictures. I don't want to get too complicated here. Really cool. Carbon pump. Carbon comes in. We make lots of sugar. Bacteria make lots of stuff for us to eat. We have our protein and we have our sugar. So now we have enough energy to keep growing and suck up more carbon. Light is the most important component of photosynthesis. Light triggers a lot of physiological rhythms in phytoplankton. Light determines the reproduction of some organisms. I mean, really. I mean, when these guys grow, other organisms rely on them, and they will grow, and they will feed. But all of these organisms are very, very temperature sensitive. Very temperature sensitive. 1 to 2 degrees Celsius in opposite directions, and they're pissed off. 1 to 2 degrees Celsius, we have a problem. They're very sensitive to temperature and pH changes. So what we add into the ocean will affect them and will affect global temperature. And I just wanted to show you some pictures of I took these pictures in Papua New Guinea and in Indonesia. And another sensitive organism to temperature and light and pollution, like various types of chemicals. A little bit too much, and they're kicking the bucket. Just some more pictures that I took. There's a whole, I mean, you got fish here because these fish are eating zooplankton. The zooplankton are here so these fish can eat because of the presence of phytoplankton. You got a whole food chain. And then you got the homes. Coral reefs and mangroves and eelgrass and oyster reefs are like homes to fisheries. And the sad thing is about coastal zones all over the world are dying because of what we're adding into the coastal zones, because we do a lot of our activities in coastal zones. And we're affecting the coastal biodiversity globally because of our activities. Not one because of temperature, and another is because of pollution. Just some more pictures I wanted to show you. Some of the places that I've worked in Southeast Asia. And my whole thing, and it's really interesting, I can turn one of the lights on, because I really, as a master's student, even back in 1994, I remember just getting a whole bunch of different critters and testing with temperature, testing them with chemicals, testing them with viruses, bacteria, and looking at how they die, basically. And I wanted to know their sensitive thresholds. And I did my master's thesis up in Woods Hole on that. I stressed out a whole bunch of different organisms, anything you could think of. And the one that was the most lethal was temperature. Mild changes in temperature, more than chemical. I mean, chemicals, bad things happened because the pH changes, but temperature was really a problem. Phytoplankton have low, like they say, phytoplankton and corals have a low boiling point.